to start. Quick. Take your seats. Thank you very much. So it is my pleasure to introduce Peter Sarnak lecture, which is joint work with Michael Rubinstein, and the title is An Undetermined Moment Problem for Eigenvalues of Matrices in Classical Groups and its application to computing root numbers and zeros of L functions. What is yours?
Thank you. Thanks very much. And I appreciate the opportunity to talk here, even on Zoom. I decided that I'm not making a transatlantic trip yet, but actually I wouldn't have been able to make it because I just discovered recently that my passport expired, and it takes like 2-3 months to get a new passport. So I probably wouldn't have arrived even if I wanted to. Anyway, thanks for the invitation. And I guess Mike Rubinstein's here with me, and well, this is joint work, and so any questions can be addressed to him as well. And I know the Zoom is sort of one-way street where I just talk to myself, but feel free to interrupt. I do that in lectures, even Zoom lectures, so I encourage you. I can hear you guys, so I think it'll work. That when you were reading out the title of my lecture, I realized how long it was. That is way too long. Anyway, it explains what I'm going to talk about, and let me just start. This work actually is work that Mike and I have been doing for a long time now, and we got stuck. We started with L functions and had trying to develop a certain algorithm that I'll explain. And it took us a long time to understand why we were failing and what the failures were all about, until we understood what the problem was really about, which is what I will spend most of the lecture on, which is this underdetermined moment problem just for classical groups. And once we understood that, we also understood certain limits as to what we can do. We were much too ambitious in a way, and I'll explain that at the end when I explain what we are doing in terms of computing zeros of L functions, which was the motivation, but there is a problem which I find just as interesting and a separate problem in what you might call geometry, non-convex geometry of moment curves. All right, so let me set it up from the beginning. So an absolutely excellent model for everything we're doing is going to be the orthogonal group of odd dimension, O2n plus 1. It's a compact group. The matrices are diagonalizable, and we're interested in its eigenvalues. Depending on the determinant, whether it's plus or minus 1, there will be an eigenvalue, non-random eigenvalue plus or minus 1, which will also eventually be the root number. So we're very interested in this plus or minus 1. And then there are 2n other eigenvalues which come in complex conjugate pairs, which we write as e to the I theta 1, e to the minus I theta 1, up to e to the I theta n, e to the minus I theta n, where the thetas are in 0 and pi. And the measure that we will be trying to reconstruct an underdetermined problem will not be reconstructable unless there will be bad situations, but we'll be asking what happens with probability tending to 1, very close to 1, in other words, almost sure. And for that, we're going to always use, unless otherwise stated, the measure on Gn, the probability measure, which is the Haar measure on Gn. And it will be pushed forward to various other probability spaces. So our parameters are epsilon theta 1 to theta n. We want to recover these, and the information we're giving ourselves are the traces of the powers of the matrices. So for j greater than or equal to 0, let me take the trace of a to the j, which is epsilon to the j, this plus minus 1 to the j, plus twice cosine j times theta nu summed over the eigenvalues. These are the moments, which are, of course, real numbers in this setting. So we have a map, which I'll call the moment map. For every k greater than or equal to 1, we have these moment maps, mkn, from my classical group Gn into R to the k. And the image is a very complicated set, as we'll see in a second, and it's all about that set. So we have a map into R to the K, and our interest is what we can say about the eigenvalues, epsilon, theta 1 to theta n, given its moments. If K is less than n, in other words, we have fewer moments, so the number of equations we would expect is n, and that would determine it, as we'll see in a second, except for the plus minus 1. But if K is much less than n, which is certainly the case of great interest to us, so if K is less than n, then this is underdetermined. As an algebraic problem, if we were just looking at the roots of these polynomials of the complex numbers, you would then have algebraic subvarieties, which are these level sets, and you wouldn't be able to say much. But because the eigenvalues are restricted to be in 0 pi, which is because we're in the classical group, and eventually this will be reflected in our assumption of the Riemann hypothesis that all the zeros of all L functions will be assumed to be on the line 1/2. So that is a very strong condition, and it's a real algebraic geometric condition. So the level sets here are semi-algebraic sets. They're defined by polynomials, real polynomials and inequalities. And we aren't interested in what we can recover when we're in this positive dimensional situation. So that's the setup. And what is it that we can hope to recover? So if you have an undetermined system of equations, you can't expect to recover the numbers, and you can't, of course, but you might be able to recover certain things. So firstly, the variable epsilon, which is this plus minus 1, is a binary variable, and we could hope to recover it, if we're lucky enough, for a typical choice relative to the probability measure. So I'll define R epsilon to be the set of y's in the moment set, which I'll show you pictures of in a minute. So MKGN are the set of points in R to the K, which are moments, which are in this image. That's a complicated subset of R to the K. And the set of y's for which epsilon is determined is R epsilon, the epsilon recoverable set. We'd like to know what is the measure of that set. It's non-empty, as we'll see, but the question is the probability near 1 or 0? Along the way, and this will be the kind of information that we can hope to recover and will recover, is I'll say that if you take a moment point, so y in MKGN in the image, the forbidden set f of y, so it's something that we'll be able to do is tell you numbers which are not eigenvalues of any matrix in the level set. So I'll say that a point f of y is the subset for which the set, so this is the f of y is the forbidden set. It's a set of values theta, which are not the eigenvalues, or including epsilon, of any matrix A which has got moments y. The complement of that set is where the eigenvalues could possibly be. So there'll be, we sometimes call that the admissible set. So capital F of y is this forbidden set, and we're trying to understand the bigger the forbidden set, the more information we have. Our enemy is that the forbidden set that we can, that in fact the forbidden set is basically empty, we can learn nothing. That is if we have too few moments. So the recoverable, the forbidden set the F recoverable set is the subset of points y in the moment space for which F of y is non-empty, for which we actually recover some information. In other words, the forbidden set is non-empty. We'll see that that consists of a finite number of intervals from the analysis that I'm about to give you. And then finally, the third thing we will try to recover is the exact count set. So suppose I try count how many of the epsilons, how many eigenvalues are there in the interval 0t for some number t between 0 and pi. If given y, I can count that number exactly, that is independent of which A lies in the level set. In other words, that's determined, then that's, I'll say t is in the exact count set. And of course, our interest is to produce t's, which are in the exact count set. And the set of recoverable exact count, so the n recoverable set, the exact count set, recoverable set in the y space, is the set for which I have n of y is non-empty. In other words, there are t's where I can count the exact number. And these problems are related because if I can count the exact number between 0 and t and see if it's even or odd, because of the way I define the moment, map here. This epsilon is plus minus 1, and this has got a 2 in front of it. So if I could determine exact counting for some t, then automatically I've recovered epsilon. So the set of n recoverable y's is a subset of the epsilon recoverable. And in fact, our method to recover epsilon is to count, to try find miracle intervals under which we can make an exact count. All right, so I hope those definitions are clear. That's what we're aiming for. As I said, we have a probability measure on Gn, which is the Haar measure on Gn, and it pushes forward to a measure on our image space, our moment space, mkGn in R to the k. And that is the measure that I'll always use. And that is the measure that is relevant in number theory because of standard conjectures about how the zeros of L functions are distributed in families. So I'll return to that later, but that's, and this turns out to be our enemy. We would do much better in these recovering problems if the measure were just sort of random points rather than the measure that's this push forward. This measure that's a push forward makes the eigenvalues very rigid and makes our life much more difficult. A feature that has been seen by us and others over the years. All right, so the only easy case of this problem is if I have one moment, and that's because the function then is just a linear function. The S1, the first moment, is just a linear function in the cosine of theta j. And all these sets are very easy to compute, but I want to think about them for a second because we can answer everything here and then see what is it we're trying to leverage in higher dimensions. So firstly, since it's linear, all these sets are convex, which will be highly the case once we get to dimension 2. So the set of moments, the values that we get for the first moment are between -2n - 1 and 2n + 1, trivially. The epsilon recoverable set are exactly the guys which are at the edges. So if I measure a moment which is either between 2n - 1 and 2n + 1, or on the other edge, -2n - 1 and -2n + 1, then I'll be able to recover epsilon, but otherwise I won't be able to. So it's already clear that the epsilon recoverable set when n is large, so this is if I have many unknowns in a linear equation and I have only one equation, I can't expect to recover anything even with these inequalities. And the F recoverable set's also easily computed, slightly bigger. So, but if I'm in this range here, I can't recover anything whatsoever. And there's always such a situation in any dimension. So the question, of course, is what is the probability of recovering? So you might think, oh, this is just polynomial 1 over n, but that's not the case. And this is a highly non-trivial theorem that I'll return to. It's a theorem in higher dimensions that limits our ability to do something in a very substantial way, which is only very recently proved, as you'll see. Okay, so asking what's the probability of recovering? So it's what's the probability of lying in these end parts? When n is large, it's more than exponentially small. And this follows from work of Johansson, Kortreet, and Lambert, recent paper, and I'll discuss it a little bit further as to where that comes from. So the point is that the measure, this push-forward measure concentrates, it becomes very much like a Gaussian concentrated near the origin, and these events at the end that you're trying to have happen are not e⁻n² small, but this small, as we'll see. So this is exponentially small or more than exponentially small. One can compute the exact probability in n equals, so when it's n equals 1, then this is between -3 and 3, so we're looking at an exact interval. I'll explain that we can compute, we actually Monte Carlo this, but you can compute it exactly. All right, so that's a one-dimensional case. And let me now state the understanding we have of this problem. This is our complete understanding. This is all asymptotic as n goes to infinity, so it kicks in quite late, which makes things in terms of feasibility a problem, which is, and this project has always been with the aim of implementing. So this is a theoretical page. So in the range, so I'm giving you the range of k and n of what we can recover with probability 1, or when is the probability of recovery exponentially small, or when is it very near 1? And the good news is that we can have very few moments, as long as so that the problem's underdetermined as long as k is less than n, or k equals n is also undetermined, doesn't determine epsilon. But as long as k is bigger than a constant times n over square root log n, so we allowed to have little over n moments, so arbitrary small number of moments in the sense of the ratio k over n can go to 0, but not too slowly, then we can recover everything with probability 1. So the geometry of the set that you're going to see in a minute is such that we can recover everything with probability 1. That is, we can recover epsilon, we can recover the forbidden set, parts of a forbidden set, and we can recover the exact count for many points with probability tending to 1. This is an asymptotic result. And most importantly, we can recover these. So if you're given y, we can recover these with a polynomial time certificate. So I'm going to explain that algorithm. It's our most important feature here. And our algorithm is not giving the complete truth, but when n goes to infinity, it does as well. It works with probability 1. That's the main statement here. So this is the positive result. And we would do much better. So this is in green because it's a different probability measure. So if instead of choosing the matrix A and its eigenvalues random in this compact classical group, if we chose the eigenvalues theta randomly independently, so that their spacings would be Poisson, then we could recover k all the way down to square root n with probability going to 1. In other words, all these theorems would apply with k all the way down to square root n. So the fact that we are limited in this very extreme range has something to do with this rigidity of the eigenvalues, making it very difficult for us to recover. It's the probability measures concentrating in the set in places which is not convenient for us. And then the following two theorems, this is a very recent theorem. I'll go over who it's due to in a minute. But if k is n to the alpha, so now I'm looking like at square root n to the alpha, but alpha is less than a third and bigger than 0, then the probability, and the main thing we always wanted to recover was the root number. Then the probability of recovering a root number is not exponential. It's not e to the minus n, but it's e to the minus n to the 1 minus alpha. So it's still not polynomially small, but rather somewhere in between exponential. So it's still extremely small. And that's very bad news for our dreams. I should say that this was a bit of a crushing inequality. And I'm sure it's true also for alpha all the way up to 1, unlike the situation with the green. So this is a very limiting feature that this probability, so the probability of recovering in this range is almost sure, and here it's extremely unlikely to recover anything. It's a dramatic change, and these are the thresholds that are fundamental for this problem. And for alpha 0 bounded, you've already seen that, then you don't just get exponential, but you get a slightly better, a smaller number, which is e to the minus delta n log n. So you've got the extra log here. If there's something you need to remember from this lecture is that the threshold is these threshold recoveries at the theoretical level.
Peter, can I make a comment at this point? So,
yeah, of course.
If I'm reading this correctly, your optimal result would be to take alpha equals 1/2, right? Because then the number of trials you need is about the same as
yeah, right. This would be when you're trying to optimize. I'm actually not even. That's if I start to twist. I will discuss. Yeah, but that's correct.
Okay, and that would lead to what we call an L1/2 algorithm here. So
that would be, in terms of your paper, which I'll get to at the end, that would give that. But we trying to understand what you can recover in with probability 1 first. Then the iteration would be what we can deal with when the probabilities are very small. Exactly. But until recently, we were still hoping that we could do things in polynomial time. Yeah.
Thank you.
Correct. Anyway, this is what we know. This is just one step. This is a probability of recovering that information if I give you a random y. All right. Now, the problem is really a problem about the moment curve. And I think this problem is a beautiful independent problem that deserves a tremendous amount of attention in terms of just inverse moment problems in real algebraic geometry. And this is really what has limited us and allowed us to understand the problem. So I want to go through it. So we take k dimensions, as we've just discussed, and we take the curve ck, which is this moment curve, 2 cosine theta, 2 cosine 2 theta, up to 2 cosine k theta, which is a curve in r to the k, when theta, this compact curve between 0 and pi, which of course is related to our problem. And for k greater than or equal to 1 and n greater than or equal to 1, we form the following subset of r to the k. We add c to the k n times, and we get a subset of r to the k. And the problem we're studying here is all about understanding a point in the summand and trying to understand what the coordinates that lead up to that sum are. So this AKN is a real semi-algebraic set. I'll give you some pictures of it in a second. K equals 1 was just an interval, as you saw. K equals 2, you can draw it yourself. It looks like this shield. And for k equals 3, and arbitrary n equations were written down by Beck and his co-authors. And this is from their paper. This is what A35 looks like. So this is what the kind of sets we're trying to understand looks like. And we're trying to understand whether a point in r to the k lies in the set or not. That's the entire problem. The algorithmic side of everything we're doing is that. And as you can see, the set is highly non-convex, and we want to exploit that. It's precisely, we'll describe the recoverable set in terms of these sets in a very clean way. But these sets are very complicated, and these probabilities are, at least to us, very difficult to estimate. So there's a fundamental complexity problem here. We don't know the answer to this. I think the answer could well be that it's true. If you, in our algorithm, we formulate a variation of this where you have subsets of this moment curve, and then it quickly becomes not NP complete via the subsum problem. But this problem, I think, okay, I don't know, but this we view as a fundamental problem, is the following recognition problem polynomial or not. So you should think of n is bigger than or equal to k. I'll discuss the case n equals k in a minute. I give you a point in r to the k, and I ask you, is that point in AKN? And if it is, you can of course show me that it is by demonstrating the summands. So it's certainly in NP, but is it in P? We don't know it's in co-NP because we don't know how to check whether a point is not in the set. But this is a very basic problem. Is this polynomial time? If it is, then every statement I have from here on out would be actually irrelevant. The complexity issue would disappear, and then the probabilities would completely describe the recovery problem. We don't know it's in P, so we're going to give an algorithm which will be run in polynomial time, and that algorithm will only approximate the answer, but it's good enough in the range to prove the threshold that I showed you, the top threshold. All right. So if n equals k, that's the first interesting case. That's where we can recover everything because we have you can use Newton's equation, Newton polynomials, and you get a polynomial one variable. You just have to compute its roots. In formulating this problem, of course, I'm doing it over the real numbers. Of course, if you really want to make it precise, you should do up to some accuracy. I'm not going to go into that. But the set A and N actually has been studied in the number theoretic context in view of Honda-Tate theory and eigenvalues, Weil numbers, eigenvalues of Frobenius on abelian varieties. Honda-Tate tells you that that's given by polynomials, characteristic polynomials, which satisfy the kind of equation I have there, but with integer coefficients, so that they are algebraic integers. And then people have tried to calculate the volume of the set and a little bit of the shape and drawn. So A and N, which is a case that we know how to recover. So we can compute if we're in A and N. So A and N is this subset of R to the N, which has been looked at by De Pippo and Howe and Kedlaya. Maybe Kedlaya even spoke about related theory in this conference. And there's a nice description by de Pupper on how of the volume, the Euclidean volume of the set. But our problem is a different problem. We have n is bigger than k. We have this underdetermined problem, and we're trying to recover the coordinates of the summands, or something about the coordinates of the summands in this range when n is bigger than k. And that's what I will be describing. So now I can describe the image. So remember, our classical group is O2n plus 1. We have this moment map. The image can be described very easily in terms of our sets AKN. That's why AKN are the most basic sets in this whole problem. So there are two components to, there's the determinant 1 and determinant -1. So the determinant 1 lands up in the set AKN plus this vector, and the determinant -1 lands up in the set AKN plus this vector, where the starts with -1 and then alternates -1 plus 1 -1 plus 1 in R to the K. And then the epsilon recoverable set is very easy to describe in this set of coordinates. It's simply the image. So the image is the union of these two sets, which you see a picture here of the union of the two sets. And the intersection, if you remove the intersection, that's exactly the points in which you can recover epsilon. So in the case of M22, where this set is this shield and it's been offset to the right and to the left, then in the intersection here, I can't recover the sign, but on the sides, I can recover the sign. So in this simple situation, we can see what the recovery set is. It's the shaded area, and its probability from a Monte Carlo, this is already a mess to compute that probability, though of course it could probably be computed exactly, is about 0.37. So the point is that even though the set outside here looks quite big, the induced probability measure, and this is our enemy, that wants to concentrate near a blob in the middle. And we're looking for the extremities in order to recover. And this is completely general. This is always what the epsilon recovery set is. So if I want to ask what's the probability of recovering epsilon in this underdetermined moment problem, it's just what's the measure of this set in our push forward measure. Similarly, the forbidden set, Fy, can be recovered as well. Described, it can be recovered in the region, in the thresholds I described, but it can be described in these coordinates very easily. Is if you have a y and you add, and you look at y plus ck, so you've got your point y and r to the k, and you add just simply ck, one of those moment curves, to it. If that meets the complement of mk gn minus 1, then we will have points in the forbidden set, and the intervals in the forbidden set that we'll be able to extract from this are exactly the intervals in which we exit the set mkgn minus 1. So at least f and the recoverable set of f and fy and epsilon are described very cleanly in this language. The exact count is a little more complicated, but it also can be extracted from this. So in terms of the moment map and in terms of these sets, this is the underlying problem. Here's a picture that Mike produced of this A22, and this is the image, and the intersection is where you don't learn anything, and anything outside is what you learn. All right, so that's our setup. Okay, now I want to describe our algorithm. Since we don't know an algorithm to decide whether a point is in AKN, we will use a sequence of linear programs, use hyperplanes, to try separate points from that set repeatedly, but looking for these hyperplanes in a particular way. So our algorithm is certainly based on linear programs. If you use, now I want to point out that there's a beautiful history here, and we rediscovered this without realizing that there's this amazing work of Chebyshev. Somehow Mike and I are followers of Chebyshev. We've written one paper about Chebyshev bias, and now this is really about this underdetermined moments. Also got something, its origins with Chebyshev. If you want to separate the set AKN, a point, to show you're not in that set with a separating hyperplane, then of course you're separating that point from the convex hull of that set. The convex hull of the set is much easier to describe. It's going to be this, just this parabola with those points all filled in, and even the much more complicated ones. And that has a very beautiful description by Chebyshev. So that would be that you're trying to understand whether you're in the convex hull, or he's looking really at reconstruction of measures, him, Markov, and Hamburger. This is an inverse moment problem. And there's a very beautiful description of that separation problem. And we use that. And you can use that as a brute force, not a brute force, as a preliminary run, as you'll see in the algorithm. It doesn't give it gives some information sometimes, but it sometimes misses critical information. However, if we start not with one hyperplane, but at least two hyperplanes, and then iterate, that's our scheme, then it turns out to be decisive, at least in this range. Asymptotically, we will always succeed with probability 1. That's the basis of that whole scheme. So the point is to start with two hyperplanes. I'm going to explain what those where those two hyperplanes are coming from in our attempt to decide whether a point is in the set AKN or not. I should say that Chebyshev has an amazing theory, which we at first thought might be extremely useful to us, but we have understood now that actually he's doing something a little different. So Chebyshev asks the question of, suppose you know a few moments and you have a measure which has those moments. We, of course, have a very special kind of measure, which is delta masses at these endpoints, but he's not putting that condition. So he's got a measure, and he wants to try estimate the measure of some subinterval in terms of these limited number of moments. And he shows that there are certain, using a theory of Padé approximations or some special orthogonal polynomials, he shows that there are special intervals on which he can essentially solve the linear program that I'm about to write down, the actual two hyperplane linear program explicitly, but only at special points. And those points are actually the opposite of the kind of points that we're looking for. So Chebyshev's sort of remarkable work there of what are called nodes and weights does not seem useful to us, though I suspect there's a deeper connection that we might have not understood. So now I'll describe our iteration. So we are given y in the moment space in that very complicated image like you saw. It's the union of the AK shifted one way and the other way. And at the new stage of our iteration, we have a lower approximation. So we will be giving an approximation. Our algorithm is trying to find the forbidden set f of y. We start with the empty set, and then we try to produce an increasing set f nu of forbidden sets, which hopefully get closer and closer to f of y. To do so, we take any subinterval of 0 pi. And so our algorithm will choose alpha beta, and we'll run over all alpha betas. So they're just two parameters here. And we'll run the following linear program. These are linear programs in real variables c naught up to ck and b naught up to bk, where we want to minimize u minus l, where u is this linear form, and l is this linear form. The minimum that we get when we run a linear program we'll call m sub j, depends on the interval j. And the constraints for the linear program are that if I form this polynomial that you'll recognize from the polynomial b, from the points b, and this polynomial in cosine theta from the points c, that the characteristic function, excuse me, of j should lie, so this would be a lower bound for the count for the characteristic function. This is an upper bound. So this is a linear program. And the important thing is I do this for all theta, not in the update in the present forbidden set. So once I'm in the forbidden set, I know there's no eigenvalue there. And so I can for free ignore those points. So to begin with, this will be the empty set. And I run this linear program. And when I'm finished running the linear program, if this minimum is less than 2, then I can make a tremendous This is the two hyperplanes that I'm learning something very interesting about. And that's because the U and the L dominate from above and below this count. So if I know what chi j epsilon is, so this is how we actually learn whether epsilon is not in the set or in the set with high probability. So this would be plus minus 1. This would be an even number. So if this interval doesn't straddle a possible solution here, then you know epsilon is actually not allowed, and the epsilon that you put, which may be 1, is not allowed, so it had to be minus 1, because we are starting off with y, which is in the moment set. Otherwise, if we know what it is, suppose we've recovered epsilon, then we're going to have this exact count. So we are doing this minimization, looking to make this number less than 2. This is where the discreteness comes in, which is not built into that Chebyshev kind of analysis that I was saying. So we run this linear program, and the minute it succeeds, the endpoints of the interval are necessarily now in the forbidden set. And then we vary alpha and beta, and we increase the forbidden set, and we iterate. So at the new plus first stage, the forbidden set is now increased by adding all the new alpha betas that we learned, and we rerun it, and we, of course, have a linear program with fewer constraints, so we do better. We start off with the empty set, we iterate it a few times. After a few iterations, it gives nothing new, as you'll see in a second in the numerics, and that's we get an approximation, lower bound for the forbidden set. And of course, our definition of success is if the lower bound, if the forbidden set is non-empty. And essentially, the minute the forbidden set is non-empty, the exact count set comes with it. This is very close to the exact count set. And once we have the exact count set, we get epsilon, and we get exact counts, and we succeed. So that's our algorithm. And the analysis of why this algorithm is going to work asymptotically is not difficult, because we just go into the algorithm, and we use a theorem. I'm going to now state another theorem in random matrix theory, which is what's the largest gap with probability 1 between the eigenvalues of a random matrix in any of these ensembles. And of course, the reason that we're struggling so much is the large gap grows, but it grows very slowly. So the eigenvalues are spaced at 1/2n if you wish, but there will be gaps with probability 1, which are of size square root log n. I'll give credit in a second. And this allows us to engineer situations where this is favorable and where mj is less than 2. And this allows us to theoretically easily prove the theorem about k over square root log n being the range in which, with probability 1, we recover everything that we set out to. We set out, we set out to do more, but that's what we will recover in this range. So the analysis of the algorithm is quite straightforward. And the probabilities, so with probability 1, we do this recovering. So that's the analysis of the algorithm. This is the algorithm, and I'll show you it in action in a minute. But before that, there are these very basic theorems in random matrix theory that should be well known. And they maybe are in some circles. The theorem 3 is very recent, and it's the one that's a bit of a killer for us. So the first theorem, and I will return to this in a moment, is what is the minimum and the maximum spacing between the eigenvalues in any of these random matrix ensembles. So the minimum spacing is with probability 1 n to the minus 4/3. This is the thesis of Jade Vincent from here in Princeton some years ago. Soon after that, the Burgade and Benarus derived the square root log n over n for the maximum spacing. That's what I'm using in the previous slide. That's for the analysis of our algorithm. The minimum spacing, I'll return to it, explain something very clearly in a picture that I'll get to in a second. And the fact that things, and this is the enemy that we, I think it was wishful thinking by us, but we'd hoped that if you give yourself k moments, and k is growing to infinity, and maybe it's growing like log n to some power, then you should be able to actually recover. And of course, that's very false. As you saw, for k equals n to the alpha up to 1/3, it's exponentially small, or almost exponentially small. And where is that coming from? This is an amazing theorem. It's called the Strong-Tego limit theorem. The first theorem of this type is due to Johansson. This is due to Treat and Johansson, and is just from last year. And it says the following, that if you take the random variable plus minus, which is on the determinant 1 and determinant minus, and you look at the moment map, in each case, this variable has mean 0. That's the measure is such that when it's got the thetas have mean -1 in the one case and +1 in the other case. So when you actually form the S's as we have to in our problem, then it's got mean 0. And there's no normalization. You do normalize here S2 over root 2, SK over root K. And these two probability distributions, they don't look at the difference between them, but they show that each one of them, and this is the most important thing, in total variation, in L1 norm, between a fixed normal variance 1 on R to the K is this small. So they estimate the total. So this is a very strong limit theorem. It's a central limit theorem, but extremely strong. There's no normalization by square root n. The number variable square root k, there's just you normalizing each guy there by root k, then you just form this measure in R to the k and the total variation in R to the k. So you can try look for sets of small measure the L1 difference, this total variation is tiny. And so the total variation between epsilon plus and epsilon minus is tiny in this range when k is n to the alpha and alpha is less than 1/3. And that means that there is just no information that and from there you can prove that these probabilities that are described for recovery are exponentially small. And this is something that we had hoped that was not the case. We'd hoped that one could do much better here not by our algorithm, but in point of fact. But we have come to understand that this is an absolute limit, and it's got to do with the rigidity of the eigenvalues. So that's a random matrix theory that we need. And now let me outline a few implementations of the algorithm. Mike has run this over years, many in the hundreds, and we sort of understand now what you can recover. And I'll just give a very quick sample of the algorithm and what you can recover. But before that, how about this recovery set when we have k equals n, when the map is either 1-to-1 or 2-to-1, and this is real algebraic geometry in action. So the map is really 2-to-1 because for each epsilon there's a set of eigenvalues. But it may be that the map is 1-to-1 because of the constraints that the eigenvalues have to be between 0 and pi. That's the real algebraic geometry in this set. And so it's interesting to understand how big must n be before essentially you recover with 100%. So the numbers you've already seen, 0.18, 0.37, those were those probabilities of those weird sets with a double shield shifted. That was this case, and this is in n equals 3, n equals 5, 2n plus 1 equals 5. So it's 0.5. And here you can see the probabilities of recovery increasing. Of course, our theorem says that asymptotically this goes to 1, but by 50, it's already 100%. According to Mike, at 100, if you're at 101, he's never ever seen a guy where you don't recover. So you recover with probability 1, the sign, instantly. But that's not that surprising. Your map's either 2-to-1 or 1-to-1, and we're saying that it's basically always 1-to-1 when n gets large. So this is, it's important for us in terms of implementing to understand when these asymptotics kick in. And the actual analysis using, so this work of Johansson and so on is very much involved in techniques that are asymptotic. Nobody works out when these things kick in. All right, let me show you the algorithm just to show you why the iteration scheme is important and how it works. So I should say. So in this here, epsilon we understand very well. We recovered that instantly. And now to avoid just throwing in that extra piece of information in the numerics, let's look at the classical group SO2n, and just then we've got n eigenvalues appearing e to the I theta, e to the minus I theta, and we want to see, we take a random such guy. So here's a random 5, so n equals 2n equals 10. So this is a SO10. It's got 5 It's got 10 eigenvalues, but they repeat, they theta j and minus theta j. So here's the eigenvalues between 0 and pi. Here are the 5 eigenvalues. This is the forbidden set. And remember that if we are in ANN, we can compute explicitly what ANN is. And if we are AN, if K is 1 less than N, then we can brute force, this is what we call we can brute force compute what the forbidden set is. And we do it for 2 good reasons. One, we want to benchmark our iteration scheme to see how much information it's losing. And second, it's good to see what the answer is, because it's we don't know what these sets look like when K is, say, N over 2. But if K is N minus 1, so in this case, K is K is, when K is 5, which is when we should recover everything, that's the forbidden set is everything. When K is 4, the forbidden set, this is the truth. This is how much it dropped. And this is a random guide to look the same if you do anything else. And if K is 3, the forbidden set drops. All right, now let's see what our algorithm does, because our algorithm was to do that iteration that I described. So here's what you get when you run it directly. So you don't get the whole forbidden set. As you can see, you're getting any part of it. And if you iterate it, you get some new points. So that's why the iteration is important. If you iterate it further, you get some new points, and so on. So this is in a low dimensional case, and this is typical what happens. We get our foot in the door, we get a lower bound that asymptotically will be information enough to get some exact counts and epsilon and part of the forbidden set. This is a bigger one. So this is 2n equals 28. So this is SO28. So there are 14 eigenvalues. And this is what the truth is. Brute force means we compute it by, since, as I said, when K is very close to N, we can actually compute the forbidden set and the actual truth of what the exact forbidden set is by this brute force method, not by our algorithm. And you can see that, of course, to begin with, you have the forbidden sets everything, and then you get less information. I want to say a word here about the lengths, the complement of the forbidden set, how long these are. And that's related to the nearest, 2 closest eigenvalues, where Vincent's theorem comes in. And we have studied, in this case of K equals N minus 1, the geometry of these curves. And there's a beautiful differential equation that we worked out that the eigenvalues satisfy, and from that we can actually understand the lengths, or how well you can approximate with probability, high probability, the eigenvalues in this situation. So you can't compute the eigenvalues exactly, but you will be able to get this n to the minus 4/3 accuracy coming from Vincent. So Vincent's theorem is very relevant in this extreme case. But the minute the level sets of high dimensions, we don't have any understanding of the geometry, or like we do of the curve case here. So this is what the true forbidden set looks like. And when we run the algorithm, we get parts of it. And when we iterate, we get better results. And so that is typical. And the bigger n, the better we do. And we know sort of when it kicks in, and this is all very important for us before we start to implement it on our main problem. All right, so I have 10 minutes, and now let me do some number theory, which is what you guys are interested in. But the limits and the understanding of this problem, this is where we started at least 12 years ago, I think it was, or maybe 10 years ago, with great ambitions. And I'll tell you that now we understand what's going on, and we're writing 2 papers. We're essentially finishing this first paper, which is about the underdetermined moment problem, and then we will have a paper where we implement this. So root numbers. So we start with a self-dual automorphic L function. Think of an elliptic curve L function of degree nu, which is fixed. I do this in general because we really are looking at a general problem here, and it's, I think, a problem that many people have tried to understand, and we've understood some part of it. So for small primes, by which you'll see what I mean by that in a minute. For small primes, we can compute the, I'm assuming the L function is an L function coming from geometry. So I can compute the APs, the coefficients or the local pieces of the L function, which are given by local characteristic polynomials of degree nu. So if it's an elliptic curve, there's one point, there's one piece of data, AP. You can compute these AP pi's in an elliptic curve, even in polylog p steps, as Rene showed us. But for our purpose of this asymptotic, so I'm first describing a soft theorem, which is an asymptotic sub-exponential algorithm. It's even okay if you only could compute these APs in polynomial in P. So if you were a higher dimensional variety and you were struggling to compute the APs, you had to actually take P to a power. That would be okay for us. Okay, I'm going to assume I know the conductor exactly. I'll return to it. I'll call it Q pi, but not the global root number. So our aim here was to try to see how quickly you can compute the root number and other of these aspects of the zeros that we've been talking about. But I'll assume that I know the conductor exactly, not just its approximate size. I'll return to that. And I want to compute the root number, but without factoring the conductor. So, and if you factor and then go and see it in local reduction, you could see whether you put +1 or -1. That I'm trying to avoid by just computing the APs for many small p's. Throughout, I'm going to assume the Riemann hypothesis. This is, if it works, then we're happy. This is an algorithm. So I'm going to assume the Riemann hypothesis for all L functions that might come my way. And in assuming the Riemann hypothesis, at least information theoretically, what we're trying to do is not unreasonable. That is, and this is exactly why we think this thought this has great power to it, is that if I have two automorphic forms which are of conductor around the same size, and I know the APs for P up to the log of the conductor squared, then I know them exactly. So if I compute the AP pi's for P up to the log of the conductor squared, in principle, I know everything now. I know the sign, and I know all the zeros. Okay, that's good to know that at least the information is there. But what we're trying to do is use that information to compute something quickly. And quickly is very demanding here, as you're supposed to do something in the number of digits, the information in the conductor, which is log of QP. So we want to try to do something in log of QP to the power. That's, of course, very ambitious. All right. Now, the other reason that Mike and I started this is Mike has been computing for, I think he has the best programs to compute zeros of L functions using this method of Riemann. And the question was to understand, can you go beyond certain thresholds? So the Riemann gold standard, which is the approximate functional equation, allows you to compute everything you want in the square root of the conductor plus little o1 steps. That's just from the approximate functional equation. This is what everybody runs. If you're doing the t aspect rather than moving the pi as we're doing here, then Iari, for example, has shown, say, with the Riemann zeta function, you can do much better. You can get a power here which is smaller than a half. You can beat this. But if you're varying pi, as far as I know, nobody's ever done anything which is better than 1/2. And I think that's rather difficult to compute things like the rank or the root number in faster than square root steps. But that's exactly what we're trying to do here. We're assuming the Riemann hypothesis, and we're asking what can we do in the conductor to the epsilon or better, sub-exponential in log of Q of pi. And the idea that we began with, and that has been used by others, as I'll say, I mean, this is probably an idea that was thought about by many, many people, is to try use the explicit formula of Riemann, Guinand, and Weil. The explicit formula, I'll remind you, is derived from the logarithmic derivative of Ls pi. So the root number disappears the minute you take the logarithmic derivative. So it's free of the root number, and you're going to try recover the root number from a few of the a pi's, and that's exactly what this underdetermined moment problem is about. So I remind you that the explicit formula is a Fourier transform duality. On the one hand, you need to know that, and we're assuming that we know what the conductor is, and a pi p's on the one hand, and then it's the Fourier transform of a measure supported at delta masses at log of the a pi p's with certain weights, and on the other side are the zeros of the zeta function, of the L function in question. I'm assuming Riemann, so the gamma pi's are real. So it's a Fourier duality, and we're trying to recover the zeros from the APs. And the reason that this has a chance of doing something sub-exponentially is that, and this is the whole point of why we began this, is that the local density of zeros is log of q pi. So it's not q pi, it's log of q pi. So the local density of zeros, which is the measure of how you might try to compute from these equations, recover the gamma pi's from any information you compute from these numbers, seems to be that you've gone down to the logarithmic scale, which of course would be wonderful if you really could do so decisively. So, for example, when you do this, and it's absolutely correct that if you want to compute, say, AP pi's, which I'm assuming you can compute quickly, as I said, and I compute, say, k of these AP pi's, where k is q pi to the alpha over 2. So square root would be alpha equals 1, which Riemann's gold standard would say you can compute everything with that. Then from the density of zeros and cutoffs of test functions, which is where we started, you find, and this is how we get to this model problem, which I think is independently interesting, is that 2n, the densities, because we were in the self-dual case with the eigenvalues being self-dual, 2n is log of q pi, and so then the complexity, the number of moments you would get, if I was computing with q pi to the alpha over 2, would be alpha times n moments. So if alpha were 1/10 here, so that I had really something which is beating the 1/2 barrier, then I would get here some fraction of n moments, and that is exactly what happens. So Riemann's gold standard comes back exactly to alpha equals 1 plus little o1, which is full recovery. So we back in the model problem, and we can reduce the real problem to the model problem by periodization. So they are essentially the same problem. The real problem is a little more complicated, and I'll say a word about that now. Okay, so this is how we came up with this problem of moments, and we have been trying to understand what you can say about, say, the root number with limited number of moments. The linear program iteration procedure is very well suited. So we don't have any other procedure other than that brute force, which doesn't exist in this number field case, but the linear program side of it works extremely well. And this leads, theoretically, we haven't implemented this yet, this was going to be paper due, leads to asymptotic subconvex in log q pi. So it says to compute the root number. You can compute the root number in one step with high probability, and you will also get an exact count for many t's, and you'll get a forbidden set asymptotically sub-exponentially. So this works. We're assuming Riemann. The equidistribution is what, when you actually do it, it'll work, and the equidistribution will be the probabilistic reasoning behind it, which is based on the fact that the zeros follow a certain distribution. These are conjectures of Katz and myself, which I think are reliable, at least in this kind of situation. And this, I think, was what Andy was asking earlier, because this is related to his work, which I'll mention in a second. Even if the above failed, so I showed you that when maybe the n is not so large and our probability of getting the root number is 1/10, or even it's very small. We always have the luxury in this number field case, if all we want is a root number, our aim has not just been for the root number, it's to see what about the zeros we can compute, and then these three things we compute in sub-exponential time. But suppose you just wanted the root number, then you could further sample by twisting your pi by a quadratic character. And when you twist the pi by a quadratic character, you don't know what the factors of the conductor are, but you do know the d, you choose d's which you know. And when you twist, the change of the root number is predictable by and there's a quick algorithm to do that by using Gauss reciprocity. So you have the luxury now of maybe having an event which was unlikely, but sampling it very often. And even if the probability were very small, this is what Iari, Keating, and Booker do in this paper that I'm about to mention, in another context, you could recover the sign. So there's no question that the root number side of this is all sub-exponential from this algorithm. The main thing you're assuming is the Riemann hypothesis, and the probability model you're assuming is your enemy, actually, as I explained. All right, now we haven't implemented this, and because the feasibility of this is quite serious. So what we're going to do, and that will be in paper 2, is to take elliptic curves. We'll need to know the conductor, or at least something about the conductor, and there's, I think, a lot of freedom here to actually only estimate the conductor, but anyway, we'll assume the conductor. So that for that we would have a model, maybe Weierstrass form, and then you compute the discriminant, then you want to compute the square free part and understand without factoring it. And here's this paper that's a very beautiful paper of Booker, Iari, and Keating to detect square free numbers using Dirichlet characters, and very similar, the most important similar part is that it uses the Riemann formula and linear programs, and does this twisting to the hilt. So they're looking for very, very rare events, and they're willing to spend a lot of time to have that rare event happen. We are not going to go that way. We really want to see something that's quite robust. So far, what's robust asymptotically is what I described, and we're hoping to show that in the second paper, where we deal with elliptic curves, that we'll be computing root numbers very quickly by this tool. But unfortunately, and this is my last slide, the underdetermined moment problem, which is what we've spent all our time on, has taught us some very basic facts. And that is, firstly, any dreams we had of beating factoring. So by the way, if you have an elliptic curve with some conductor and you set it up so it's square free and you have multiplicative good reduction, then the computing the root number is the same as computing Mobius, which is really where I'd love to compute Mobius quickly in polynomial time. And we are going to get stuck, probably. I think Andrew was already pointing out where we would get stuck. We haven't really worked this out, because this would be pushing these very rare events to their limit. But we will certainly get stuck. We won't get better than sub-exponential, and we'll get stuck at something like, or maybe worse, than what the factoring algorithms do. The other thing we learned from this is we have now a lot of data on just the underdetermined moment problem, and we have to see what's feasible, because things kick in, and if n is 1,000, which is where things might work very well as far as recovery from our algorithm, the q is then exponential of that, and that's sort of something that you can't start to do in this world. So this has been a very important learning experience for us, and so far our concentration has been on the underdetermined moment problem, but it's clear where we will go from this. And it is very much related to this paper of Booker, Iari, and Keating, which was written roughly when we were also thinking about these. And I'm sure Andy can say more about that. All right, I think I'll stop there. Thank you very much.
Thank you very much. Are there any questions in the audience?
I have a few comments, but in the interest of time, I'll just make the main one. Actually, so Guy Fieri had a very similar idea. I think if I could paraphrase your viewpoint of this, it's that you want to take advantage of the discreteness of the eigenvalues of the zero.
Right. Absolutely. Yeah, that's.
Yeah, Guy had the same idea, and he was also very optimistic that we'll get down to polynomial time. I told him he was crazy. Then he worked on it, and eventually I came over to his side. So something similar is written up in our paper, just in a different language. So we expressed it as integer linear programming problem.
Yeah.
So my main point is you can express it in that language, and the conclusion there is, if we knew how to solve integer linear programs, as quickly as we can over the reals, right? Then you can do this very quickly. But yeah, probably.
So, I mean, the way I would put it is a little different. Indeed, Iari was at the Institute when we were working on it. We discussed this, and then he came, I guess, to you guys, and you worked out this variation with the square root, which with a square free, which I was very impressed by. They are very much related. It was what we were doing also, but I think where we're sacrificing, as you say, is that the eigenvalues are integers, but the real sacrifice is that we don't know what the zeros of we're assuming just Riemann here, and that's this that the analog of that the thetas are between 0 and pi. We don't know any as you the big sacrifice where we've moved into this continuum of this group, and it's exactly what you're saying, that we've lost information there. And in that context, the theorem of Johansson and his co-workers show that you can't recover certain information in the context of the full random. So, the actual zeros of L functions would be a discrete subset, as you're saying, but I don't have a clue as to how to recognize it, which is maybe a different way of saying what you're saying. Yeah, but of course the tools that we're using are very similar to yours, but we're trying to not just infer one object like the sun. We're trying to say what. So it's a basic question. If I give you a global algebro-geometric thing, and I give you the conductor, and I give you a lot of APs, what can you say about the object? And if you know square root of the conductor APs, you've got the object completely back. Riemann tells you you need much less. Complexity-wise, this is, it's the same idea. I should say the thing in your paper that's very impressive is you looked at this RSA number, which you pushed it a little. Yeah.
Maybe can I make just one more comment?
So there was a question now going on respond, and I'm sure you will have lots of questions.
Yeah.
So let's take one quick question.
So you looked at the probability of being certain of your guess, but have you also looked at the probability where if you had to guess without necessarily being certain, how often did you guess right? I don't know if that's
Say it again. The probability of being certain. Are you asking kind of what's the conditional probability as you learn more moments?
Yeah, essentially, yes. Like if you.
Yeah, right. So we haven't looked at that in the range that we succeed, because we're quite happy there. But in the range where we know we're going to fail, in other words, in this range, here, the answer is the conditional probabilities tell you nothing. In other words, there's no information in, you see, well, you learn, so the fact that these two probability measures, plus and minus, are both within a normal distribution with total variation, which is this, says there's nothing more to be inferred there. Yeah. So in this range, I haven't, and that would be interesting, but in this, and that would be relevant in terms of the feasibility. These results are all asymptotic and they kick in quite late, which is annoying. And where you're saying that's relevant is, especially for epsilon, where I'm allowed to sample, that is something we have to tackle in paper 2, yeah. But this part, I think, is, at least once we've embedded our problem in the continuum with the compact group and what you can recover. So the conditional probability will not have changed. In other words, if I have n to the 1/3 moments, it's kind of shocking to me. If you run the linear program, that's clear. In other words, any convexification of the problem, that's clear. But the set, you would still think there's some extreme event that you could try find some conditional probability, it's like a voting scheme, and you're looking for some hint whether it's +1, some little hint where the probability of now being +1 rather than -1 is increased. But this says, forget it, you can do nothing. Well, unless you're willing to sample this many times. 1 over that many times. That's what Booker I'll do.
Thank you. Sure, there will be time to ask so many questions, but we're running over time, so let's thank the speaker again.
Again, thank you.